Welcome to this sixth video in the lecture series on textile printing. This is actually the second part of our topic of weft straighteners. In this lecture, we are going to talk about the roller or the cylinder weft straightener. This is by far the most common type of weft straightener that is utilized in textile industry to remove weft distortions. As far as the working of a roller weft straightener is concerned, there are two aspects to it. The fabric from which the weft distortions have to be removed is scanned by different types of sensors. This scanning is done to detect the layout of weft threads. In other words, it is the scanning step in which the type of distortion and the magnitude of distortion is detected. So if you look at this image here, this part or this array of small modules is actually a set of different sensors. The second aspect in the working of a weft straightener is that once the distortions are detected, the fabric is passed over multiple rollers, which are called correction rollers, because these are the rollers which remove the weft distortions. The orientation of these rollers can be changed according to the detected distortion. So in this image here, this set of rollers is actually the correction arrangement. Let's now look at the working principle of a roller weft straightener. The working principle of a roller weft straightener is stated as you can see here. The correction or removal of weft distortions is done by lengthening the path of weft threads that have advanced from their ideal position. This statement can be written in other words, and in that case it will become that correction is done by shortening the path of weft threads that are lagging from their ideal positions. Let's now try to understand this working principle with the help of some images. But before that, recall that most common distortions are simple bow and skew. So we are going to understand this working principle in the context of these two distortions. Let's first talk about a bow distortion. In order to remove a bow distortion, the fabric is passed through a weft straightener, a roller weft straightener, in this format. So this arrow over here is representing the direction in which the fabric is traveling. The fabric is guided by certain rollers, and then it is made to pass over a curved roller which is known as the bow roller. Notice in this image that the central part of the weft has advanced from its ideal position. In other words, this portion of weft threads is leading compared to the other parts of the same weft thread. So compare this part in the circle to, let's say, this part over here or this part. So this is the advanced portion of the weft thread. In this case, the fabric is made to pass over a bow roller shown here. And because of the orientation of the bow roller, this central part or the advanced part of the weft thread will travel a greater distance compared to the other parts while it travels over the bow roller. Similarly, if we look at the skew distortion removal using a roller weft straightener, then once again you can focus on this part of the weft threads in comparison to other parts such as this one. This part has advanced from its ideal position. This roller over here is the skew correction roller, which is tilted accordingly. So this advanced portion of weft threads, as it passes over this tilted skew roller, will travel a greater distance compared to the other parts of the weft threads. In this way, the portions of the weft threads which have advanced from their ideal position are made to travel a longer distance compared to the other parts of the same weft threads. And therefore, after passing over these correction rollers, as shown in the image here, these advanced portions are at the same position as that of the other parts of the weft threads. Now, in the previous lecture, the most important part was the working principle of different types of weft straighteners. So, with the help of some images, I tried to explain in the previous lecture that how the two types of weft straighteners, that is the roller weft straightener and the pinwheel weft straightener, remove these weft distortions. But because it's a slightly tricky concept to understand, so I thought maybe while reviewing the previous lecture, I can present another example that might help you in understanding the working principle of both types of weft straighteners that we discussed in the previous part. So let's first talk about a roller weft straightener. We are not going to discuss its parts in details. The purpose of this review is just to, as I've just mentioned, it's just to provide you another example that will help you in understanding the working principle. So let's see how it works. To understand the working principle, we can consider the example of two cars that are traveling on a road. So we have car A and car B, let's say, and these two cars are of course traveling on a straight road as shown in the image here. Now let's assume that car B is ahead of car A, let's say by 2 kilometers, and both these cars are traveling at the same speed. So if car A is at 50 kilometers per hour speed, then car B is traveling at the same speed. Now you can relate this diagram with a fabric, let's say. So the road is actually a fabric, and the two cars are 2 points on a weft thread, let's say. So now point B is, let's say, 2 inches ahead of point A. It cannot be 2 kilometers, of course, in case of a weft thread. So let's say it's 2 inches, point B is 2 inches ahead of point A. So that becomes the skew, of course, as shown here by the red dotted line also. So there is a skew between the positions of B and A. Now let's say these two cars on the road reach a roundabout. So of course car B will reach this roundabout first, and car A will still be 2 kilometers behind car B. Notice that both cars are traveling at the same speed. That's very important, right? Only in that case car B will reach the roundabout uh, ahead of car A. Now let's say the driver of car B is asked to take the exit and cover an extra distance as shown here. So let's say this extra distance is 1 kilometer either side. So 1 kilometer up and 1 kilometer down. So the total extra distance the car B travels in this way is 2 kilometers. Now, of course, when car B will reach back to this roundabout, car A will already be here. Just because car A was 2 kilometers behind car B, but car B traveled an extra 2 kilometers. So when these two cars reach the exit of the roundabout, then these will be at the same position. And now from this point onwards, the two cars will be uh, at the same position on the road. So that's exactly the working principle of a roller weft straightener. But in order for these cars to be at the same point after car B has traveled an extra 2 kilometers, it's important that while car B was traveling this extra distance of 2 kilometers, it was traveling at the same speed. So you can apply the exact same rule on this fabric and this skew distortion that is present in it. Point B is 2 inches ahead of point A. So by some means, point B should be made to travel 2 inches more than point A while maintaining the same speed. So maintaining the same speed is not a problem in case of fabric, because of course the entire fabric web is, when it's moving in a fabric, all the points on the fabric are at the same speed. So this extra distance that we want a leading point to cover in comparison to the lagging points is achieved with the help of the skew and bow rollers, as it was discussed in detail in the previous lecture. So just because it's easier for me to draw a skew roller, so let's consider that example. When in normal operation, the fabric is passing over a skew roller, which is straight. If there is no distortion in the weft, if there is no skew distortion in the weft, so the blue dotted roller that you see here is a skew roller. But if a skew distortion starts to appear in the fabric and one of the points is ahead of the other points, then this skew roller is tilted accordingly. So continuing with the numbers that we assumed in the previous slide, if point B is 2 inches ahead of point A, then the tilt in the skew roller will be 2 inches at least. So when the skew roller is tilted, it appears like this. If I try to draw it, it's no longer straight, it's now tilted by 2 inches. It's like this. And again, once again, due to this tilt of the skew roller, point B covers a calculated extra distance compared to point A. Right. So if I superimpose the tilt of the skew roller on this image over here, so this skew roller, which was initially straight, is now tilted if a skew distortion is detected. It's like this. The green lines show the tilted position of the skew roller. So that was an example that I could think of, which actually mathematically proves that if a point is made to travel a larger distance compared to some lagging points, then after covering that extra distance at the same speed, the leading point and the lagging points will all acquire the same position. Hopefully it's much clearer to you now. It's just numbers, simple mathematics, so you can just have a closer look multiple times to completely absorb this concept. So that was the working principle of the weft straightener. Now let's see which are the important parts in a roller weft straightener that perform this correction operation. So a set of parts in a roller weft straightener can be referred to as a scanning arrangement. As we have discussed briefly before, a scanning arrangement is a set of sensors or cameras that detect the layout of weft threads. In other words, these sensors detect the type of distortion and calculate the magnitude of distortion also. The working of these sensors is completely automatic. The operator does not have to do anything or any settings usually. Different types of sensors are available for roller weft straighteners. In one of the more common types of scanning arrangements, there are a fixed number of scanners or sensors that are stationary. That is, during operation, the scanners are not moving or traversing. In this case, only the gap between the scanners can be adjusted. So for instance, if a narrow width fabric is being run through a weft straightener, the scanners can be moved close to each other. But if on the same weft straightener, a wider width fabric is being run, then the gap between the scanners can be increased by the operator. This type of scanning arrangement looks something like this. So this is one sensor or a scanner. And as you can see in the image here, for this particular weft straightener, 4 scanners are shown. It's not necessary that there are always 4 scanners. Depending on the width of the machine, there can be 6 or even up to 8 scanners mounted on a frame like this. If you look closely at this scanner, it has 2 parts. One is the part from which some sort of light, for instance infrared light, is radiated onto the fabric, and on the other side there is a receiver. The fabric is constantly passed between these 2 parts of a sensor, and depending upon how the radiated light passes through the fabric, the distortions are automatically calculated and measured. Another type of a scanning arrangement consists of a single scanner, and this scanner traverses from one side to another constantly as the fabric is passed through it. The major benefit of this type of a scanning arrangement, in which a single scanner traverses from one side to another constantly, is that in this way, scanning of all the points over the entire width of the fabric is possible. This image will further clarify this point. So the single camera is over here, and as you can see in the image, while the fabric is being passed through the weft straightener, this camera is constantly traversing from one side to the other. So the yellow points that you see are all the different scanning points. So the entire width of the fabric is scanned. Or in other words, every single point over the entire width of the fabric is scanned if the sensor is traversing constantly from one side to another. The other set of parts in a roller weft straightener is the correction arrangement. As briefly mentioned before, the correction arrangement is the set of parts which are actually responsible for removing the distortion from the fabric once the distortion is detected. So in a roller weft straightener, the correction arrangement consists of a set of bow rollers that are there to remove bow distortions. So in the image here, these red rubber coated rollers that you see are the bow rollers. And then there is a set of simple steel rollers which are known as the skew rollers, and they are there to remove skew distortions from the fabric. You can notice in the image here that multiple skew rollers are mounted on a single frame. Usually, the common configuration for a roller weft straightener is 3 skew rollers and 2 or 3 bow rollers. However, please note that the manufacturers of roller weft straighteners offer a wide range of roller straighteners with different numbers of correction rollers. Now let's further clarify this point with the help of a video. So of course, we have a display panel. The display panel shows the type and the magnitude of the distortions in the incoming fabric, and it also displays the weft distortions that are present in the fabric that is coming out of the weft straightener. These are the sensors. Now the machine is not working right now. However, even if the fabric is being processed through the machine, these sensors will be stationary at their places. The three shiny steel rollers that you see on this side are the skew correction rollers. And on the other side of the machine, you can see these red curved rollers that have a rubber coating on them. These are the bow correction rollers. From this video, you can also establish an idea of the size of this machine. As I said before, it's a relatively small unit and can be easily accommodated within a stander. So let's now talk about the bow correction rollers. The bow correction rollers are actually quite similar to the spreader rollers that are used very frequently in open width continuous processing machines for crease removal. You might have studied about these types of rollers when you studied about a bleaching machine. In a bleaching machine, just before the squeezers, we usually have these bow rollers to ensure that there are no creases present in the fabric as it goes through the squeezers. So the bow correction rollers are very similar in structure to these spreader rollers. If we look at the structure in a bit more detail, then in these curved rollers or bow rollers, there is a stationary shaft which is of course curved in the profile as shown in the image here, and an outer rubber sleeve which is free to rotate on this curved shaft. Now the curvature of the shaft cannot be changed because it is a solid steel shaft. So how much it is bent, of course, that's a fixed parameter. However, the shaft itself can be rotated to change the effective curvature of the roller. In the case of a weft straightener, this movement or rotation of the bow correction rollers is done automatically by the actuators according to the detected distortion. Then we have the skew correction rollers. The skew correction rollers are very similar to simple guide rollers that are used in open width continuous processing machines. If you are aware of the structure of these guide rollers, then you know already that these guide rollers have a smooth, shiny surface, which is of course metallic, and these rollers are free to rotate about their axis. As shown in the image here, the skew correction rollers have a smooth metallic outer surface. In a weft straightener, multiple such rollers are mounted on a frame. And this frame can be tilted with the help of actuators. Once again, the tilting of this frame on which these skew correction rollers are mounted is done automatically by the machine controls based on the signals that they receive from the sensors. Recall the different types of skew distortions. We can have a left-hand skew or a right-hand skew. If the sensors detect a left-hand skew, the frame on which the skew rollers are mounted will be tilted from the left side. Similarly, if the sensors detect a right-hand skew in the fabric, then this frame on which the skew rollers are mounted will be tilted accordingly. Let's discuss the working modes of a roller weft straightener. By now, I have already mentioned a couple of times that the usual operation of a roller weft straightener is completely automatic. So the sensors are constantly detecting the type and the magnitude of weft distortions, and the signals from these sensors is sent to machine controls, which then change the orientation of the bow rollers or the skew rollers accordingly. The roller weft straighteners can be operated manually also. This is not usually done for removal of weft distortions. In fact, when a roller weft straightener is used for removing design deviations in a printed fabric, and if that particular weft straightener is not provided with appropriate sensors, appropriate type of sensors, then the operator will disengage the sensors, and the operator will visually analyze the design deviation in the printed fabric, and then the operator will adjust the orientation of the bow and skew rollers accordingly. A roller weft straightener can also be used for automatic correction or removal of deviations from a printed design or any other pattern on the fabric. In this case, special sensors are used that are able to measure and detect the deviations in the printed design or pattern. The rest of the working is once again automatic. So the deviation in the design that is recorded by the sensors is calculated, and the machine controls then automatically adjust the orientation of the bow and the skew rollers to remove deviations from the pattern in the fabric. So if you notice, the primary difference between a roller weft straightener, which is mainly used for removal of weft distortions, and a roller weft straightener, which is mainly used for correction of pattern, is that of the sensors. The type of sensors in these two types of roller weft straighteners is different. As far as the correction arrangement is concerned, that we have just discussed, which consists of bow and skew rollers, that part, that is the correction arrangement, has a similar structure in both cases. Now for a weft straightener, of course, the most important aspect is its corrective effect. In other words, how much bow or skew can be removed by a particular weft straightener. There are, of course, limits. For proper corrective action of a roller weft straightener, it is important that the fabric is under proper tension as it passes through the weft straightener. This is required to ensure that the fabric is completely wrapped onto the correction rollers. If the fabric is running loosely over the correction rollers, then no correction will be done. In addition, the corrective action of a roller weft straightener depends on number of correction rollers, that is, how many bow or skew rollers are present in the weft straightener, the geometry of these correction rollers, and interestingly, the corrective effect also depends on the width of the fabric that is being processed. Let's have a look at the calculation of corrective effect in percentage in great detail now. The geometry of the correction rollers is one of the aspects, as discussed in the previous slides, which dictate the corrective action of a roller weft straightener. It is obvious that the geometry of correction rollers is fixed by the manufacturer. So once you have purchased a roller weft straightener, you cannot change the diameter of the correction rollers. In case of bow rollers, let's say, you cannot change the curvature of the bow roller. If you recall that slide in which we discussed the structure of bow roller, I mentioned that the curvature of the shaft is fixed, which means that the curvature of bow rollers is also fixed. In case of skew rollers, again, if you recall the structure of the skew rollers, then the maximum tilt of the frame on which skew rollers are mounted is also fixed depending upon the design of the machine. Manufacturers provide a graph for the calculation of corrective effect in percentage using their Weft straightener. This graph looks something like this. Let's look at the different aspects of this graph, so that in the next slide we will look at an example of how to use this graph for calculation of the corrective effect percentage. The vertical axis here is the corrective effect in percentage. The horizontal axis here is this ratio, width of the fabric divided by nominal width of rollers. Nominal width of rollers simply refers to the working width of the weft straightener. This line here you see, the green one, is the line that we use for calculation of skew correction percentage. And this curved part or curved line in the graph, which I've highlighted in blue, is the line that we use for correction of for calculation of bow corrective percentage. This point will hopefully become more clear when we look at an example in the next slide. So this is the graph provided by, let's say, a manufacturer of a weft straightener. Let's consider an example. Let's say the fabric width is 100 inches. Let's assume that the machine width, which is the nominal width of rollers or the working width of the machine, is 120 inches. Let's assume further that the bow in the fabric is detected by the sensors and it's calculated to be 4 inches, while the skew in the fabric is found to be, let's say, 6 inches. Now, in order to calculate the corrective effect, we first need to calculate this ratio, width of the fabric divided by nominal width of the rollers. So we have fabric width of 100 inches and the machine width 120 inches. So this ratio is of course 0.83. You can approximately consider it to be 0.8. Now let's see how we calculate the skew corrective percentage of this weft straightener. We have calculated this ratio 0.8, that's on the horizontal axis. From this point we extend a line vertically upward until it intersects the skew straightener line, and then we trace this point horizontally to intersect the corrective effect axis. So from here you can see that the corrective effect for skew is approximately 80%. You don't need to be very accurate here because the axes on the graph are not very accurate. So for one skew roller, if let's say there is only one skew roller in the straightener, then it can remove 80% of the incoming skew. So 80% of 6 inches. One skew roller will be able to remove 80% of 6 is 4.8 inches. So one skew roller will be able to remove 4.8 inches of skew from the fabric. Now, normally we do not use a single skew roller as you have seen before. So we divide the total distortion among multiple rollers so that we don't have to tilt the frame too much. Now let's see how we calculate the bow corrective effect. Once again, we start from this point, point 8. We trace a line vertically upward, not all the way up to the skew straightener, sorry. We start from point 8 and go vertically upward until we intersect the skew straightener curve, and then we trace it horizontally until the line intersects the corrective effect percentage. So from this graph you can see that the bow correction in percentage is approximately 50%, let's say. So one bow roller of this particular weft straightener can remove 50% of the incoming bow. That's 50% of 4 inches, which is of course 2 inches. So when this fabric passes over one bow roller, 2-inch bow is removed. So let's say if we have two bow rollers, then the total of 4-inch distortion will be removed. 2-inch from one bow roller and the remaining 2-inch when the fabric passes over the other bow roller. So now in this example, you can do a small exercise. Keeping all the data same, that's the machine width 120 inches, the bow 4 inches, and the skew in the incoming fabric to be 6 inches, just change the fabric width. Solve the same sort of numerical by considering a fabric width of, let's say, 80 inches. And if you do the calculations, you will see that just because this ratio will change, it will be smaller than 0.8. So the maximum corrective effect of one bow and one skew roller will also reduce considerably. We can discuss this in the interactive session that follows this lecture. So let's recall what important observations we made during the calculation of the corrective effect. Of course, the working width, that's the nominal width of the rollers, is a constant for a particular weft straightener. As the fabric width changes, the corrective effect of a weft straightener will also change. More specifically, as the fabric width is reduced, the corrective effect of the same weft straightener will also reduce. There is another thing that you can observe if you revisit the graph of corrective effect percentage, and that is that for any given weft straightener, the nominal width or the working width of the rollers is the same. That is, the working width for bow rollers and skew rollers is the same. However, the corrective effect in percentage of bow rollers is always considerably less than the corrective effect of the skew rollers. All of this has to do with the geometry of the rollers and the way they work. So of course, in order to ensure that the incoming distortion in the fabric is completely removed, a logical choice is to provide multiple correction rollers on the machine. Another advantage that we get if we use multiple bow and multiple skew rollers in a weft straightener is that individually each of these rollers has to be adjusted only slightly. This is particularly important to maintain the alignment of the fabric as it passes over the correction roller. Let me explain this point a bit more. Let's say if the skew in a fabric is 4 inches, and let's assume that you are using a weft straightener which has only one skew roller, then in order to remove this incoming skew of 4 inches in one pass through the weft straightener, you will have to tilt the skew roller by 4 inches. Now it's not easy to control a fabric when it is passing over tilted rollers. In fact, this is not something convenient from the point of view of handling the fabric in an open width continuous processing machine. But if we have, let's say, three skew correction rollers in that weft straightener, and the incoming distortion or skew is 4 inches, then we divide 4 by 3, which is approximately 1.34, let's say. So the frame of the skew rollers has to be only tilted by 1.34 inches instead of 4 inches. So this reduced tilt in the this reduced tilt in the skew rollers or in the bow rollers help us in maintaining the alignment of the fabric in the machine. The third type of weft straighteners is called a combination weft straightener. As the name implies, it's simply a combination of a roller weft straightener and a pinwheel weft straightener, both of which we have discussed in the previous slides. So this is what a combination weft straightener looks like. In this image, if you look at the upper part of the machine, then it is simply a pinwheel weft straightener. And if you look at the lower part of the machine, then it is a simple roller or cylinder weft straightener. We have discussed both of these in the previous slides. So a combination weft straightener is simply the two weft straighteners stacked on top of each other. As you can expect, there are obvious advantages of doing this. In a combination weft straightener, we get the combined performance of the two types of straighteners. Recall that a pinwheel weft straightener is capable of removing wavy distortions, while a roller weft straightener or a cylinder weft straightener cannot remove wavy distortions. So in a combination weft straightener, the pinwheel part removes the wavy distortions and the roller part removes simple bow and skew distortions.
Let's now look at a summary of what we have covered in this lecture. So when we want to prepare a fabric for printing, we do have to perform the usual pre-treatment steps such as singeing, desizing, and bleaching, etc. In addition to all these routine and usual pre-treatment processes, we have to remove weft distortions before we print on a fabric. This is because if we print on a fabric which has weft distortions in it, then later on, as we move towards the finished product and we try to remove the weft distortions, we can end up with a fabric which has distorted wefts in it. Weft distortions are removed using machines called weft straighteners, and the types are a roller weft straightener, which is used to remove simple bow, skew, and simple combinations of bow and skew. We have another type of weft straightener called a pinwheel weft straightener, which is known to remove all types of distortions, including what are known as compound distortions. And then we have combination weft straighteners that provide us the best of both of these weft straighteners. This marks the end of our discussion on weft straighteners. Thank you for your attention.